it's all me.
So we'll pick it up right where we left it off before the review and the exam. We should have the exams graded by the end of the week as usual. But otherwise, when we left it off, we were exploring how functions actually worked. And I gave a demonstration where we had this program that had these two values, n and m, and wanted to compute the average. So instead of just doing it directly like you normally would, we made a function that was called average that we called, and then a sum function that summed them together. So we had a function that called a function that called a function. And the way that this works is by keeping track of this program stack. So more formally now, what is a stack? Well, a stack is a LIFO data structure. LIFO means last in, first out. The analogy that I gave last time was this stack of dishes that's growing upwards. Now, if you've got a stack of dishes and you want to take a dish from the stack, you don't take one at the bottom or in the middle or somewhere. You risk, tipping the stack over and it all comes crashing down. What you do is you take it off the top. So the basic operations are that you pop from the top of the stack, right? This is that you remove the topmost element, or if you're going to put a dish on top of this in the stack, you don't shove it in between, you put it on the top, and that's called pushing. You push an element to the top of the stack. Right? Those two basic operations in the stack. And the reason you do this is because it allows you to keep track of what are called breadcrumbs. And we literally call these breadcrumbs because it's just like Hansel and Gretel. The story of Hansel and Gretel, two kids that were taken into the forest to be abandoned. Well, the idea is that they took a piece of bread with them and they took off little breadcrumbs so that they could find their way back home. As they went into the forest, they didn't want to get lost, and so they left these breadcrumbs down. If I'm in the call stack here, how do I know to get back where I came from? In other words, once the sum function is done functioning, how do I return back to the calling function, the average function? All you have to do is take the stack frame and pop it off the top. And then you're right back to where you came from. When the average function is done, how do you get back to the main? Well, again, you just pop off the stack frame and you're back right at the main. So function calls function calls function. A new stack frame is created at the top and pushed onto the top. When you return from that function, it is popped off the top, right? And stacks have way more applications than just a call stack, but you get the idea here. Again, every time a function is called, a new stack frame is created and placed on the top of the call stack. We also call this the program stack. And the great thing about this is that all local variables and parameters in a function are stored in that function's stack frame. Right? One function, each function, can only see its own stack frame. That's why it didn't. There was no problems here if I had two variables called A and two variables called B. They existed in completely different stack frames, and so they were completely different functions. This is how scoping works, right? This is how scoping actually works. Right? You can have multiple variables of the same name, but they exist in different stack frames, and therefore they have their own scope, their own context, right? So once a function is done executing, its stack frame is popped off the top, and control is returned. This is why we use the keyword return, returned to the calling function. Right? It's all magic, and it's not really magic now that we've demystified it. It's just stack frame on top of stack frame on top of stack frames. Exactly the same mechanism that two medieval children used to find their way back out of the forest. Right? So the question that comes up is, can a function swap two values? Right? This is where we left it off last time. And for that, I've got an example over here. Not this one, but over here in Python Tutor. All right. I've set up an example here where we've got two variables A and B with the values 10 and 20. I print them out in the main. I should expect 10 and 20. And then I try to call this function called swap. Let's take a look at what happens inside that function. When I get there, I print them out, right, just to make sure that I received 10 and 20. I then create a temporary variable, and I put A into this temporary variable so that I can put B into A, and I can take that temporary variable and put it back into B. Thus, I have swapped them, right? And I prove that it works by printing it out here. 10 and 20 will actually be swapped. But are those the same 10 and 20, A and B, as in the main? I printed it out again, and you'll see that it doesn't work. Again, let's understand why. Let's walk through this line by line here. I've got 10 and 20. When I print them out, as expected, it's 10 and 20. But when I call that swap function, what happens? A brand new stack frame is created on top of it with two new variables, A and B. These are not the same variables, right? They receive the values 10 and 20 because that's what the values were of A and B when we called this function. And in fact, it does actually successfully swap, right? 10 will go into temp, 20 will go into A, 10 will go back into B. So when I print them out, they indeed are swapped. But what are swapped? The copies. Right? What about the originals? Are they touched at all? No, because this stack frame is completely unaware of these variables over here. If I were to rename these X and Y, it would be absolutely clear that these are completely different variables, right? But they're still completely different variables because they're in different stack frames, right? So my goal here is not if you pass by value, right? In other words, when a function is called, copies of the values of any parameter, argument, or input variables are passed to the function, not the actual variables. But can we? And the answer is yes, we can. Can we pass actual variables, right, in order to have a true working swap function? And the answer is yes, we can. In fact, C is one of the very few programming languages that lets you do this. And because it's quite dangerous because it allows you access to low-level memory. But in order to do this, what we need is first our pointers, right? Pointers. Right. So how does memory work, right? Memory in a computer has both an address and contents. And this is where my second picture of the day comes in. Right? Here is an example of memory. You have an address and contents. When I store pi, for example, in memory, I'm storing that somewhere in memory. It's got to be located somewhere. In fact, since it's a double, right, it takes 8 bytes. And so 1, 2, 3, 4, 5, 6, 7, 8 bytes is where this is actually getting stored. Here's an example of an integer being stored. Remember, an integer only takes 4 bytes. 1, 2, 3, 4 bytes. And it's being stored in this area of memory. If I have a single character is only 1 byte. So if I store capital H, it only needs 1 byte of storage here. Now, what is the address here? It's just a number, right? It depends on how much memory your system has. It depends on how it gets addressed. But at the end of the day, it's just a hexadecimal number, right? It's meaningless to us, right? But the contents is what we focus on. I'm storing pi, or I'm storing this integer here, or I'm storing this entire string, okay? So an address is where it's an address. An address is a numerical designation of where data is stored. The contents are the actual data, right? So there's a big difference between int a equals 42 and the memory address at which it's stored. In the programs that we've been working with up till this point, in fact, let me go ahead and go over here and get rid of this. Ignore that for a second, right? Do you see any memory addresses here at all? No. Likewise, you don't even see any binary, right? 42. We're able to write this as a 42 in base 10 because we all had 10 fingers and 10 toes. That's how we think. That's how we count. But when it actually gets into a computer, it is converted to just a bunch of bytes, a bunch of bits, a bunch of zeros and ones. Right? That's all opaque to us. We don't have to worry about those low-level details. Likewise, we don't have to worry about where this is stored in memory. Now, before I introduce pointers, let me show you that it is indeed stored somewhere in memory. Printf, the contents stored in variable A are %d end line. This should be familiar to everyone. This is just regular old printing of variables. Printf, the variable A is stored at memory location %p, and we'll understand that in a second here. In fact, we probably already do. What did I say that we were going to introduce? Pointers. So if you want to print a memory address, you'll want to print a pointer, and the placeholder for doing that is %p. Now, this will be magic for a second until we realize, wait a second, I've seen something like that before. Ampersand A. Where have we seen that? Ampersand with scanf. And I told you at that point that it was just magic, that you needed it for then, right? Well, now we're going to demystify that. What that does is it gives you the memory address of that variable. Let me go ahead and compile this and see what it looks like. GCC demo, there we go. And when I run this, we're going to get this mysterious hexadecimal number that kind of corresponds to the example over here, right? It's just some number, right? It's completely meaningless to us. What we are concerned about is the actual contents of that memory. But we can get access to where that memory is located and where that memory is stored. Now, let me run this one more time, but before I do, let's take some bets. Do you think the exact same thing will be printed or not? All right, it's 7FFFF, ... whatever, 6F4. Do you think the exact same thing will get printed? No. In fact, every single time I run it, it's going to be slightly different or majorly different. Why is that? We just covered how programs actually work with the call stack. What gets loaded at the very bottom of this call stack? The program code. Likewise, any global variables or static content gets loaded on top of that. At any one point in time, there are hundreds, if not thousands, of processes running on my computer at once. I can show them to you all. I can show all of them to you. If I run this utility called top, it's going to show me all the current running processes. Right? So it'll get refreshed every couple of seconds here or so. But those are all the programs that are being run right now. Several nodes, bash, sudo, t, sh, socat. And every single one of them is using memory. So memory is getting swapped in and out and changed hands like thousands of times every single second. That means that every single time that I run my program, it gets loaded up in a different memory location every single time. Consequently, the address at which A is stored is also changing, okay? Because that's how memory works. Once, on one iteration, or in one instance, it could be loaded up in memory location 1, 2, 3, 4. When I run it again, it'll get loaded up in 4, 5, 6, memory location, right? So, contents and data are, the contents and the data are different from the address at which it's stored. Right? Pointers in C allow you to actually access and manipulate the contents of memory through the memory address. Right? So normally, the way that we've been working with variables up to this point is if you want to change the value in A, you just do it. A is now equal to 101. And if I were to print that out, the contents would be different, but the memory location would still be the same. Check it out. 42, and then it changes to 101. This is what we're used to. But the memory location stays the same. In other words, I am jumping to this memory location, and I am changing the contents of it. But what I can do now with pointers is directly access the memory address. Not the thing on the right-hand side, the contents, but the thing on the left-hand side, the address. I can get access to that now. Right? How? So let's walk through an example here. Let's walk through this example right here. Right? So I'm going to declare, give myself some more room here, declare a pointer variable that can point to A. Right? So the way that I'm going to do that is by creating int ptr to A. Right? Now ptr to A is just a variable name. I'm going to make it a pointer to A. But that would be a regular old variable. To make this into a pointer variable, I'm going to put a star in front of it, or you can call it an asterisk. We just call it star. Right? This creates a pointer variable that can point to A. But be careful. What does ptr to A currently point to? Question mark. All right? Now for this, let's go back and review. If I just say int x, what value is stored in x right now? Question mark, right? In fact, if you look at the Python tutor visualization here, let's jump all the way back to the beginning. What's it using before it actually gets allocated, before it actually gets set? Question mark. I don't know. It could be anything. Likely it's going to be 0, but it doesn't have to be. It's uninitialized value. So it could be some random value. It could be garbage. It could be dead beef, right? Ultimately, it's question mark. So, same answer up here. What does it point to? Question mark, right? Who knows? All right? It could point to a memory location that doesn't exist. That would be bad. A memory location that exists but does not belong to you, or your program is what I mean, right? Or it could be a memory location that belongs to your program, but that you should still not mess with, right? Imagine if we just messed with whatever we wanted in our own memory. Here's our own memory. What if I started messing up with the programming code, changing it? You can do that, right? Whether or not it gives you what you want, right? You're throwing the dice and taking a gamble there. But you can do whatever you want. Right? Now, do you remember what would happen if you try to scanf into x %d here, and then what? X? Yeah, let's go ahead and go with x. Right? X. So let's go ahead and compile this. First of all, it's complaining for a reason now, and that we'll understand. But let me go ahead and try a.out. And it's I didn't write a prompt, please enter a number. But let me go ahead and write in a number 1, 2, 3. Do you remember what's going to happen if I forgot that ampersand? Segmentation fault. What's going on there? Without that % sign there, It's accessing a memory location that either doesn't exist, a memory location that exists but doesn't belong to me, or I'm just screwing up my own memory, in which it's completely fine with it. It's probably one of these two. The operating system is saying, wait a second, you're trying to access memory that doesn't exist or doesn't belong to you. That's a huge security risk. What would happen if you could write a program to access the memory of another program? What if that other program that you're now accessing holds cryptographic keys, private keys? What if it holds passwords? What if it holds a bunch of other sensitive information? Should any old program be allowed to access the memory location of every other program? No. A good operating system will detect that and then cause a segmentation fault. There's a segment of memory that you've illegally tried to access, so you're at fault here and we're going to kill your program. And that's what happened here. The entire program got dumped, right? It got killed. So, what is it pointing to right now? Nothing. Let's make it point to something that is invalid, but at least safer. It is best practice to initialize a pointer to null. Right? Null is a very special memory address. PTR2A is equal to null. It is not a valid memory address. It's just it's a signal to you that this is not a valid pointer. It's not pointing to anything valid. Okay? And then you can check for it. You can check for null. Right? For null. All caps, that's how you write it. If PTR2A is equal to null, then be careful. Printf error, you cannot access this memory. Or do something with it, right? Do something other than trying to access that memory, because that's not actual memory that you can access, right? All right, well, that's how you can initialize it to null. How do we actually make the pointer point to A, the variable A? Right? We do it as follows. PTR2A is equal to, let me try this first of all, and let's think about this. This is wrong. What is that thing on the left-hand side again? What kind of variable is it? A pointer. It's a memory address. What is the thing on the right-hand side? What kind of variable is that? Just a regular old variable, right? We cannot conflate these two. An address is not the same thing as the contents that are stored at that address. So I need to make sure that these are compatible. How do I take a regular old variable and turn it into a memory location so that I could print it? I put an ampersand in front of it. Or how do I make it so that I can get the memory address so that it can get this pointer to point to it? Something like this, the ampersand, right? The ampersand in front of a regular old variable gives you the memory address of that variable, right? It is the referencing operator. Why reference? Well, it's a reference. When we say memory address, when we say pointer, reference, all of these things are the same thing. Okay? Let's visualize this in the same Python tutor over here. So let me go ahead and edit this code, and I'll leave the swap there for a second, but let's go ahead and get rid of all this. And let's go ahead and recreate those variables. Int A is equal to 42. And then I've got a pointer to A. I need int star pointer to A, and I'll make it point to A. Let's visualize what this looks like. It will literally show it as a pointer. Why do we call it a pointer? It's pointing to something. It's referencing something. So let me go ahead and initialize 42, the contents of A, 42. Now, there's your pointer. Right? All it is an arrow that is referencing this memory location up here. Right? So that's how we can make a pointer point to something. Okay? Here's some pitfalls that you need to be careful of. Careful. Do not make a pointer point to an invalid memory address. Right? For example, PTR2A. The example that I showed before that was wrong, you can do something like that. What will that do? This makes the pointer point to memory address 42. How likely is it that memory address 42 belongs to you? Probably very unlikely. It probably belongs to the operating system, right? Another pitfall is this would make the pointer point to memory address 101. If I just did ptr to a is equal to 101. And if you blindly compile all of this stuff, let me compile it, shut off all the warnings. It's perfectly valid C code. It'll let you do whatever you want with it, right? But when I turn on all the warnings, of course it's going to complain about this. And now let's read this with a little bit more discernment now that we understand the syntax. Why is it complaining about ptr to a is equal to a? Well, remember, what is the thing on the left-hand side? It's a pointer. It's a memory address. What is the thing on the right-hand side? It's a regular old variable, right? What is a regular old variable in this context? Just an int. What is a pointer in this context? It's an int star. And it's saying that these two things are not the same thing. One is int star, one is int. And it's saying that you're going to have a bad time trying to do something like this. In fact, let me show you by grabbing this up here. There we go. Now, instead of printing out A, I'll print out ptr to A. There. And let's spell location correctly. Okay, there we go. All right. And let's run it. All right, there we go. The contents stored by the variable A are 42. I did not change those. Right? But the variable A is stored at memory location 065. What is 065? Let's look up a hexadecimal converter. Hexadecimal converter. There we go. Online here. We can go ahead and try to convert that. Guess what the value that holds? 101 in base 10. Where does that come from? My mistaken code up here that is trying to make it point to memory location 101. Right? Now, nothing is wrong here with this code. It runs perfectly fine. But let me try to dereference it. Right? So, ampersand is the referencing operator. Right? It takes you from a regular old variable and it converts it to a memory address. The opposite operation is the dereferencing operator, right? which takes a memory address and converts it right back into a regular old variable. Right? And the symbol, or syntax I should say, is to use an asterisk or a star. Right? What I mean by that is, let's go ahead and print the contents pointed there. The contents at memory location %p are %d. Now let me go ahead and print out ptr to a, because that's the pointer variable. And then what is stored at that location? ptr to a. I put a star in front of it, and that takes the pointer variable and converts it right back to a regular variable so that it can be printed. Now, as it is, again, do I have access to memory location 101? Probably not. So predict what's going to happen here when I try to run it. Same thing that happens when you run scanf, missing your ampersand, a segmentation fault. I'm trying to access memory location 101, and it's not going to work. All right? So let me fix this. All right? Let me fix this by making ptr to a point to a again. Right? Remember, that's the correct way of doing it. When I do that, of course, it's still going to complain about the code above, but when it runs, we'll see that it's now pointing to this actual memory location, not memory location 101, but what is stored at that memory location? 42. So I've taken it all the way back around. Right? You started out with a regular old variable, then you created a pointer that can point to that variable, and then I went all the way back around to, okay, well, I'm just dereferencing that pointer here. Right? Dereferencing also allows me to change the value. ptr to a is equal to, let's think of something else entirely, 23, say. There we go. That's Jordan, right? All right, yeah. So what have I done? I've changed 42 into 23, right? I could have done that by doing this, right? But this is the fancy way of doing it, right? With a pointer. And let me show you that it actually did work, right? Same memory location, but 42 has now been changed to 23. Why would you ever want to do something like this? We could just change it to 23 by saying A is now equal to 23, because it allows us to now do this swap function, okay? So let's edit this code and show you, and let me show you what I mean. All right, let's go ahead and get rid of all that, and let's get rid of this. Now, what if instead of regular old variables, what if these were pointers to variables? This was a pointer and this was a pointer, okay? And I'll go ahead and get rid of this swap because we can always visualize it. Right? Now, I want to get what's stored in memory location A, and I want to put it into this temporary variable here. The left-hand side is a regular old variable. The right-hand side is a pointer. So how do I convert a pointer into a regular old variable so that I can access what's at that memory location? Dereference it. Right? Likewise, how do I change this pointer variable into a regular old variable so that I can assign it a regular old value? Dereference, dereference. Dereference that to finally put temp into it. Okay? Now let's come down here to swap. Can I pass A, which is a regular old variable here, to this function which expects a pointer? No. So how do I take a regular old variable and translate it into a pointer variable? What was the opposite of the star? Ampersand. These are opposites of each other, just like plus is the opposite of minus and vice versa. Multiplication is the opposite, or the inverse of division, right? And vice versa. This, star and ampersand are the opposites of each other. You can take a regular old variable and translate it into a memory address. You can take a memory address and translate it into a regular old variable. Now let's see this operation. There we go. So 10 and 20 are successfully stored in those regular old variables. I print them out, 10 and 20. Now I'm going to call the swap method, or the swap function, excuse me. Right? These are no longer integers. They are pointers to integers. When I jump into this function, you'll see that these are not regular old variables. They are pointers pointing to a completely different stack frame. Right? Now that I have pointers to these things, I can manipulate them directly. Whereas before, one stack frame is completely unaware of variables in another stack frame, now we are aware of them because we have their memory addresses. I've got this pointer to A, and I've got this pointer to B, and I can manipulate their contents directly. I can jump to A, grab 10, and store it in a regular old variable. I can jump to B and change its content, or jump to A and change its contents. I can jump to B and change its contents. See how that's changing in the main stack frame? Right. Now when I return to main, guess what? They're successfully swapped because I was able to access them through their pointers. Right? This means that I can now pass by reference. Right? So actually, let me grab this code before we lose it. Right? And I will put this over here as the examples. Right? See. There we go. So, using pointers as function parameters allows us to pass by reference. Right? That means that memory addresses of variables are passed to the function. Right? Since the function has the memory address, it can jump to those locations and directly manipulate the contents of that memory. Right? This enables us to write a proper functioning swap function. Right? And it enables us to do a lot more. Right? Now that we have low-level access to memory, we can now directly access and manipulate the contents of memory, right? And it opens up a whole new world of possibilities that we'll get into as we go along here. It allows us to do dynamic memory and arrays. It allows us to do proper error handling. It allows us to return variables by reference, to take variables by reference, et cetera, right? So there's pointers. Again, as a summary here, some observations. Again, going back to the original use of scanf, right? Remember that when we used scanf, we needed to put an ampersand in front of x. Why? Because we were not passing x as a value, whatever was stored in x. We wanted x to be filled with a value, right? We used an ampersand to pass by reference so that scanf could read the input from the user and then jump to the memory location of x and put the value in there, right? If it couldn't jump to the memory location of x, it couldn't give you back whatever the user was typing in. If the user's sitting there mashing the keyboard, entering in 101, right? How are we going to get that back to your calling function that called scanf? We're not doing it by the return value because it works in a different way. It works by calling by reference. We're going to give it a memory location instead. The analogy that I like to give is that passing by reference is essentially passing a bucket, a shared bucket, right? You give the function a bucket to fill with a value, right? Oops, sorry, there we go. So again, the way they view this is through memory. I'm going to give you the bucket stored at this memory location. Now that we have a shared piece of information, this 7FFF, whatever, blah, 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 right? We can both jump to the memory location and directly manipulate the contents. I can put stuff in that memory location. You can take stuff out of that memory location. So that when we need to read something in from the user, I'll say, store it in that bucket over there, that memory location. Scanf is then able to read from the user and put it into that bucket. And because we both have a reference to that bucket, we both have pointers to that bucket, we can go ahead and read whatever is stored in that bucket, in that memory location. Right? Passing by reference, again, essentially passes a bucket. Careful, manipulating uninitialized variables or even null or invalid pointers will lead to a segmentation fault. In fact, always remember what Bret Hart said. ... So, does anybody know who Bret Hart is? Bret Hart, null pointer video. There we go. There we go. It's a great video. Back from the 90s, there was a wrestling game. And to promote it, they shot this video. He's a wrestler, an 80s wrestler, but bled into the 90s, I think. And so they were developing this game. And just as a joke, I don't know if the audio will work here. I've got HDMI, so hopefully the audio will work. But I also have a million ad blockers, so there we go. All right, that's a little loud. There we go. So Bret Hart here is talking to all the programmers. He's just a dumb wrestler, but even he can see that the programmers are dumb. There you go. So the next time you try to dereference a null pointer, you're going to get a segmentation fault. When you do, just remember Bret Hart and hit yourself over the head. I am dereferencing an invalid pointer here. Right? That you have to have a valid pointer that points to a valid memory location that belongs to your program. Otherwise, you're going to have a segmentation fault and kill the program. Right? So just remember what Bret Hart said. Right? You're dereferencing a null pointer. Let's look at a brief summary. You're going to get plenty of practice as we go along. A pointer is a memory address or a reference to a memory address. We use both of those terms interchangeably. A pointer variable can be declared using the star symbol. Right? So int star a. Right? Oh, let me call it PTR2a. It is best practice to initialize a variable, a pointer directly to what you want it to point to, or if you don't know, then make it point to null. NULL, all caps. That is defined in the standard library. So if you've gotten in the habit of always including the standard library, you're golden. If you've not gotten into that good habit, then make sure that you do, because if you don't, then it won't compile, right? If you're going to try to use null and you forget to include the standard library, I think that it won't even compile. Let's try it. Yep. There we go. Error. It has no idea what null is. Why? Because it's the input-output library. Oh no, it's in the input standard def library, which is in the standard standard library. So let's restore that stuff, and now it'll compile. Oops. Oh no, I lost my. Oh, here's a good teaching moment. I accidentally lost my terminal. What do I do? Oh, did I just minimize it? I don't think I just minimized it. What do I do? Terminal. New terminal. There we go. And then go back to where I came from. There we go. GCC. There. All right, so if you ever accidentally lose your terminal, I did a quick key to close it. Otherwise, if you accidentally click that X there, then you can always come back up here, terminal, new terminal, right, and restore that. Right? All right, so make sure that you're including the standard library. To convert a regular old variable into a memory address, /pointer/reference, use the referencing operator, which is the ampersand. Right? To convert a pointer into a regular old variable, in order to access or change its value, the value stored in its location, stored at its location, use the dereferencing operator. And the dereferencing operator in this case is the star. Right? So how are you going to remember which one is which? Right? You don't. I mean, you use it 50 times and you'll finally have it memorized. Otherwise, we don't require memorization here. I always tell the story back when I was taking calc many, many years ago. I never remembered what the derivative of sine was. Was it cosine or was it negative cosine? Cosine. You remember it. Great. I never remembered it. And to this day, I still don't have it memorized. So the way that I made it up, I think I do. I always have to look it up. But the way that I memorized it, or the way I had to memorize it for calc class at least that year, is I put it up on a post-it note, and I remembered it. Derivative of sine, cosine. Derivative of cosine is negative sine, right? I just put those two up until I memorized. I saw it so many times that I just remembered it. Same thing here. Which one is which? Ampersand or star? Ampersand or star, right? Well, first of all, your compiler will tell you if you're wrong, but it's just something that you'll remember after 50 times of using it, right? It's not something you have to memorize, but you'll memorize it by virtue of using it, okay? Don't make pointers point to things they shouldn't point to. For example, the examples that we just did, right? If I make it point to memory location 42, or I make it point to memory location 101, or if I do something like this. Let me go ahead and get rid of all of this stuff. All right, there we go. So let me go ahead and create a double pointer, and I'll just call it P, right? And I'll make it point to A. Right? Let's go ahead and try to print that out. Printf, memory location %P stores the value, and then it's an integer, right? So I'll try to, or it's a double, right? So I'll go ahead and try to treat it as a floating point number. So P and dereferencing of P. Let's go ahead and try to compile that. First of all, hopefully the compiler will warn me about it. GCC demo with all the warnings turned on. In fact, it does, right? Wait a second, these are not the same thing. The thing on the left-hand side is a double pointer. The thing on the right-hand side is not a double pointer, right? Let's find out what happens here. Let's run it. I don't have that in my history, so let's go ahead and do this. Is it going to print out the value 42? Probably not. I wonder what it's going to print out. Absolute garbage. Now why? How many bytes are stored in A, or are used to store A? 4. 1, 2, 3, 4. But my pointer thinks it's pointing to a double. How many bytes are in a double? 8. So in other words, what the pointer is going to do is it's going to assume that these 4 bytes are part of it, but also that these 4 bytes are part of it. Now, 3, 2, 3, 2, 1, 2, 3, 1, and then half of pi. What is that? Gibberish. Garbage. Right? Likewise, what would happen if I switch this around? What if I said that I've got a double value, pi, 3.14159, and I try to create an integer pointer, p, and I make it point to pi? Right? Now let's try to interpret that as a integer. There we go. Again, same warning for the same reason. You can't have an integer pointer needs to point to an integer. A double pointer needs to point to a double. If you switch them around, you're going to get gibberish garbage values. Right? 266631570. Where the hell is that coming from? Right? Well, it's coming from the fact that you've got 8 bytes here, but you're only paying attention to half of them. And whatever is stored there is being interpreted as that random number. Right? So make sure that you are pointing stuff to the proper way. Right? Yep. Right. You can create any type of pointer. You can have an integer pointer for integers. Right? You can have a double pointer for, who would have thought, doubles. Right? You can have char star. Right? For characters. Right? But you need to make sure that they're all being pointed to the correct thing. Okay? All right. Any questions on this so far? No? Then let me grab this code and at least give it to you in the notes here, because this really frees up a lot. For example, let me go back to our finance utils here. There we go. I didn't have any error handling when I made these functions. For example, what would happen if you called get monthly payment and you had a negative principal, right? So error conditions. The principal could be negative. What about 0? Should we allow that? Probably not. Why? You want to take out a loan for $0. All right, why are you standing here at the bank? Right? The bank is going to look at you and say, I move along. Right? So less than or equal to 0. Right? What about that annual percentage rate? What if the annual percentage rate is, ooh, wow, what if it's less than 0? You can have, by the way, you can have 0 percentage rates. Those are great car loans, right? They're incentives to buy new, brand new, really expensive, overpriced cars that you don't need, right? So less than 0. A loan that charges -%, take that loan. Why? They're giving you money to borrow money, right? Borrow $1 billion, right? And now you're making money, right? And borrow as much as you can. Versus an annual percentage rate or greater than 1, right? In fact, that's usury. That's illegal. I don't know what the top level percent is, but anything above 20% is definitely usury and not ethical. I don't know about legal or not, right? But anyway, certainly greater than 1, right? What about number of years? What are some bad inputs for that value? Negative values, okay, so num years is less than 0. What about equal to 0? Here's your loan, pay it back immediately. Right? That doesn't make any sense either. So we'll go ahead and say that those are the error conditions, but am I handling those at all? No. I can't handle them. Why? How would I handle them? Right? So I want to know what the monthly payment is under any of these conditions. What value could I give back to you to indicate that there's an error? -1? Okay. 0? Okay. You could interpret those as errors. But what we're going to do now is that since we don't need to return the value, we can pass a value by reference. What I could do is I could redesign this function, double result. How does that help me? Again, the analogy of the bucket. Somebody gives me a bucket. I can now compute what the monthly payment should be, and I can put it into this bucket. Instead of returning the result, I can say result is equal to that thing. Except, remind me, how do I take a pointer variable and change it into a regular old variable so that I can put something in that bucket? There we go. That frees up the return value. Right? What I can do now is I can return an error code, right? And that's not going to be the actual code that we use, but now I can return an error code. The convention is that 0 is going to be no error. Right? Non-zero is going to be some kind error. Right? In fact, it could be 1 is an error with the principal. 2 could be interpreted as an error with the APR. 3 could be interpreted as an error with the num years. And then you can go back and you can handle each one of those in a different way if you really wanted to. And that's where we'll pick it up on Wednesday.